So, welcome to Chemistry 111. Quick reminder, test was technically due Wednesday. There's a few people who haven't turned in the test yet. Get that to me, ideally by today. If you're struggling, you had opportunities to come get help. You still technically have opportunities to come get straightened out. So, if you're not getting help that you need, I don't know what you're doing. I'm going to start today by going over a little news article that from January's edition of C&EN News, which is Chemical and Engineering News. But I'm finally getting up reading some of my issues. I'm going to make a copy and put this on the bulletin board for anyone who cares to read. But this is kind of an interesting article that kind of emphasizes why it's important to actually understand chemistry, even if you're going into something like nursing. You want to understand the concept behind these things and not just have them be a black box of magic of how this actually works. So the article is titled Sensors Misread O2 for Black People. Essentially, the oxygen sensors, the pulsometers that they clip on your finger, your ear, or whatever, is going to tries to read how much oxygen is bound in the blood. It's a nice, non-invasive method to look at how much oxygen your body's getting. They clip it on, like say you've inhaled some CO, carbon monoxide, which binds to the blood. You can tell, like, well, how much oxygen they're getting. Right now, it's typically being used to see if someone needs to be hospitalized, if someone needs to be put on like a ventilator due to COVID. So there's a little problem here. There's another way they can test it where they take a blood sample and it like essentially detects gas pressure as they degasify the blood. They essentially pull the oxygen from the blood and the blood sample, and they can figure out how much oxygen was bound. That's kind of a little painful. It's kind of, you have to get essentially a blood draw for that. So if you can use this pulsometer, it's actually preferable. However, the way the pulsometer works is essentially it shoots two little wavelengths of light that penetrate the skin. They don't penetrate much. They don't penetrate far, but they get far enough to go into the blood. They reach those, and it's going to measure the absorption of how much of this light gets absorbed. That's why they clip it on like ear or finger, somewhere where it's particularly thin. It doesn't need to go too far. So the idea is it uses two different wavelengths of light. One like an infrared wavelength and one like, let's see, I'm trying to remember here. One a red and one an infrared wavelength. Essentially, one of them will identify unbound blood vessels, or essentially blood cells that don't have oxygen bound with one wavelength, and one of them will detect when the oxygen is bound. And by looking at that ratio, they can figure out how much oxygen is in the blood cell. However, that you're making the assumption that everybody's skin is absorbing the same wavelengths of light, the same degree. And like most things, this is made using white people as a standard. So if you compare it to other skins and other skin colorings, they may absorb light at different wavelengths. And especially, I guess, the black skin would absorb the infrared a little bit more, if not a lot more. And so a lot of people, a lot of African-American people they're reading a higher oxygen count than they think. And so they're being improperly treated. They should be hospitalized when they're, oh, you're fine. And that's maybe one of the reasons why there is seems to be a higher mortality rate among people of African-American descent, because you're not getting a good reading on how much oxygen their body is getting. So they're not being treated hospitalized when they need to be. They're not being put on the ventilator when they need to be. And really, this is almost obvious if you understand how it works. It's absorbing two different wavelengths, and you think about it, does everyone's skin absorb the same wavelength? If I put a red shirt versus a blue shirt, would they absorb the same wavelength? And the answer is no. So, but if you're just like, I clip it on this and it reads the oxygen amount, you don't know why it's not working. You don't, but the engineers behind this that understand how it works, once you understand the process by why it's working and what it does, it seems, well, this is a pretty big flaw that should be addressed. And even someone in nursing, if you understand what that's going through, you can better be able to treat that. So maybe in this case, we either develop something that, or have some way to calibrate for that, or you have to simply stick with more of the blood draws for people with darker skin so they can get more accurate reading and treat them properly. So I'm going to make a photocopy of that and put it on the bulletin board if anyone actually cares to read it. If not, it'll sit up there, whatever. Hopefully until we no longer have to worry about COVID in our classrooms. But so I just want to share, that's just another example of why even nurses, chemistry is kind of important to even nurses, because you're looking at how does this technology that we use in the hospital work. So I was just reading that literally this morning, and I'm like, oh, that would be a good thing to share. That's really quite interesting. We had last left off in chapter 7. We were talking about electron geometry. Electron geometry looks at how many things are coming off the center atom and thus gives it a shape based on how many things. Now, in the case of H2O and CO2, they have completely different shapes. They have completely different properties. Now, why is that? If you, at first glance, you would say they should be the same. You have H, O, H, 1, 2. C, O, 2, 1, 2. But what we're forgetting is something that plays a big part. That what we've got here is lone pair, 3, 4. So this guy, just by having two molecules coming off it, has a completely different electronic geometry from the first place. Even though there's two atoms coming off of each one, two atoms coming off of each one, their total number of things coming off of each one is completely different. So yeah. Now, not all structures will fit into those 5 basic shapes that we discussed. Now, this will be the difference from the bonding domains and the non-bonding lone pairs. Even though the water has 4 things coming off of it, and it would have a base shape of tetrahedral, the overall shape would be something we call bent structure. And this bent structure is going to be different from this linear structure of CO2. That's going to be responsible for water's interesting properties. So the initial shape that we'll start off, all of them will have a set electron geometry. That's going to be our 5 base shapes. We'll start by always identifying one of the 5 base shapes, regardless of what domains we have. But then we'll have to modify it based on the lone pairs, as we'll see in a minute. So if I have 3 domains, that could be 3 single bonds, could be 2 bonds and a lone pair, could be 1 bond and 2 lone pairs. It would make a general shape of trigonal planar. 5 domains would be trigonal bipyramidal. Doesn't matter if it's 5 single bonds like PF5. It could be 4 bonds and a lone pair, which would be like SF4. Could be 3 bonds and 2 lone pairs like CLF3. Or it could be like 2 bonds and 3 lone pairs, like I think like a noble gas, like xenon F2. All these would have 5 domains and would have the same basic shape. But we're going to get to molecular geometry in just a second. Oh, stop for a second. Okay. So the molecular geometry, by its definition, look at the molecules or the elements on a whole and not necessarily the lone pairs. The lone pairs still take up space. They're still there, but when we look at the shape and define the shape, we're defining the shape based on the atoms. Based on the atoms. The electrons, the lone pairs are still there. They still take up space. In fact, they actually take up more space than bonding electrons. They take up more space because they're not constrained within a bond. So they're actually going to expand a bit, and it's going to change the bond angle a bit. Change the bond angle a bit. But this atom-centered view is known as our molecular geometry. So when we look at this in the lab, for lab 4, lab 4 will not be a hard lab. Lab 4 will be busy work, but it's like a ton of practice with drawing Lewis structures, a ton of practice with drawing shapes and determining molecular geometry. Technically, we could actually do, once we finish this chapter, you could do the lab during spring break. Am I going to make you do the lab during spring break? I'm not a monster. You can use that chance to do whatever you need. Catch up on homework, do an online lab, but no, I'm not going to force you to cram another lab in there. We'll wait on that. But we're almost ready to do lab 4, even though we won't get to it for a little while because of our missing. Okay. So how do we determine our molecular geometry? First thing we're going to do is we're going to determine our electron geometry, or electronic geometry. But we'll start with a Lewis structure. We always need a valid Lewis structure. So first thing you need to do is be able to draw a Lewis structure. It doesn't matter if you do high formal charge or low formal charge, expanded octet, it will have the same Lewis structure. We'll determine the electron geometry by figuring out how many domains it has. Now, at this point, we will differentiate between the lone pairs and the bonded electrons. We'll say how many bonding domains does it have? How many lone pairs does it have? One of the key things, and this still trips up some people, is the sum of the bonds and the sum of the lone pairs should add up to your electron domains. If you have 5 electron domains and 3 bonds, you should have 2 lone pairs. You can figure out one if you know the other, because they should add up to the electron domains. Now, based on the number of lone pairs, we will modify the shape from our starting geometry so as to maximize the distance. And this will be our molecular geometry. Now, just because, and here's one thing that will always trip people up on a test. Don't forget to draw in the valence electrons. I will give you a structure like SF4, and you will think, oh, S, center atom, F, there's 4 Fs, it's tetrahedral. There's 4 items coming off of it, it's tetrahedral. But no, it's actually trigonal bipyramidal because it has a lone pair. Sulfur should have 6 valence electrons. Sulfur, when I just say SF4, you don't see that lone pair. You don't hear that lone pair. It's implied to be there because sulfur is group 6. But without drawing the molecule, you will miss it. So just because lone pairs aren't obviously there in the chemical formula doesn't mean they aren't actually there. You have to remember your valence electrons and draw your structures out. Draw your structures out. So BH3 and NH3 have different shapes. BH3 has 3 valence electrons and is stuck making 3 bonds. NH3 has 5 valence electrons in the nitrogen and can make 3 bonds and 1 lone pair. You've got to be able to draw the structure and see the difference. Now, here's our basic molecular shapes. This is a chart that is in Lab 4. I recopied this chart because it's a very good chart. It's very helpful. So what we'll see here, this first column is the same as our electron geometry. The steric number here reads, how many electron domains does it have? 2 electron domains, it's going to be this row. 3 electron domains, it's going to be this row. 4 electron domains, it's going to be this row. 5, 6. Now, technically, there's crazy expanded ones for 7s and 8s, but those are like transuranic compounds. So we're not going to deal with the lanthanides and actinides and those really heavy molecules that can do that. So we'll never have to worry about those. But we'll go up to 6. Base geometry. This is their electron domain shapes and their bond angles. This assumes 0 lone pairs. Electron geometry is all this column. 0 lone pairs. Here's the thing. If the molecular geometry, if the structure has 0 lone pairs, then molecular geometry and electron geometry are the same. If there's no lone pairs, they match. But okay, let's look at it. 1 lone pair. If there's 1 lone pair on trigonal planar, we remove this atom, and it doesn't matter which atom you move. You could rotate it around, and it becomes a shape we call bent. Some people might call it angular, but bent is good enough. Or tetrahedral structure, which is the equilateral triangle, the 4 equal faces. If we remove one of the bonds and put a lone pair, it becomes what we call a trigonal pyramid. It's kind of a squat pyramid, but it's a traditional 3-sided pyramid. And if we remove 2 bonds, it becomes also bent. This is your basic structure of water. HOH with 2 lone pairs. Water is a bent structure, which is going to differentiate it from linear structure of CO2. Trigonal bipyramidal is where we start to get really hard. So when we remove 1 bond, we have something we call a seesaw or sawhorse. To do this, you really kind of have to see this. You have to turn it on its side, and you'll see like, oh, here's the 2 legs of seesaw, and here's the seats on both sides. Or you can see the two legs of a sawhorse, and there's your flat board that you're using. If we remove two bonds, you're essentially covering up this side, and you're seeing what's called a T shape. Once again, it's kind of on its side. But you can see there's the cross of the T, and there's the leg of the T. And if we remove 3, it becomes linear. So we removed all 3 from here, and so now it's just a straight line. Each time we're removing electrons, we're trying to keep these electrons as far away, this lone pair as far away from each other as possible, which is why we're removing them from the center and not the top. The center has a 120 degree bond angle. When we put them in the center like this, they can be farther away from each other than if we put it at the top where they're 90 degrees away from something. So octahedral, which is our double square pyramid, if we remove one bond, it makes a square pyramid. So it's just flat square right here with the pyramid peak. Now if we remove a second set, instead of square pyramid, it becomes square planar, a flat square. We just see this square right here. We remove a third set, which we typically won't see, but if we did that, you would get T shape. And if we removed a fourth set somehow, we would get linear. So there's our molecular shapes. So what we have to do is determine the electron geometry, so essentially which row we're in, and then determine how many lone pairs, and adjust our geometry to match the number of lone pairs. 0, 1, 2, 3, etc. Okay, we lost the lights, that's fine. Determine the molecular geometry of xenon F4 and Cl F3. Xenon F4 and chloride F3. What we got to do. Okay. Xenon F4 and chloride F3. The reason I used Fs is so we can't do any crazy expanded octet stuff on the outside. We're just going to want the maximum amount of, we want to get an octet to the outer atoms. Everything else is fine. Some of these guys are going to be a little weird. Xenon, for example, that's a noble gas. Typically doesn't want to make a bond, but yet here we are. We're going to make a bond. Noble gas, so that's 8 electrons plus 7 from fluorine. 7 times 4 is what, 28. 28 plus 8 is what, 36. So let's start. Xenon. It doesn't need to be pretty, the Lewis structure. We'll determine the shape after the fact. So we can start with there. That uses 8. We're down to 28. Let's see if I can. Sorry, I'm just trying to figure out. No, there we go. Is that better or worse? Is that too much of a glare? Okay, 28. Okay, and there we go. Okay. So each fluorine needs 6 electrons to have an octet because it has 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 4 electrons left. We need to put them around the center atom. That's the only thing to it. Does it matter that now xenon has 12 electrons around it? No. Xenon is allowed to have an expanded octet, so we are perfectly okay. Now we need to determine the electron geometry. How many things are coming off of xenon? 1, 2, 3, 4, 5, 6. 6 electron domains means it is octahedral. So let's go ahead and draw this, the basic octahedral shape coming off of here, and we'll put the atoms in a second. Okay. Now the next part is how many of them are bonds and how many are lone pairs. We have 1, 2, 3, 4 bonds, 2 lone pairs, bonds, 2 lone pairs. So we have to put in, it doesn't matter where I put these in. I can put the lone pair here, but I have to put the lone pair on the opposite side. That's the important thing. Now this guy is a flat square. The base shape here is square planar. Square planar has 4 bonds, 2 lone pairs. Looking at ClF3. Cl is 7. F is 7. 7 times 3 is 21, plus another 7 is 28. Move it down. Cl. I'm going to just put an F, F, F. That uses up, of my 28, that uses up 6. We're down to 22. Each fluorine needs 6 to get its 8. 2, 4, 6. 10, 8, 10, 12. 14, 16, 18. 4 electrons left. 1, 2, 3, 4. All used up. Is it okay that the chlorine has 10 electrons around it? Yes, it is row 3. It is expanded octet. It is allowed to have an expanded octet. There's nothing we can do about it because of the nature of this molecule. It's not like we're shifting double bonds. We've made single bonds to everything. There's no other way to bond this so that it's all one molecule. There's no other way to draw this so it's all one molecule and still has the same structure. So here comes the electron domain geometry. 1, 2, 3, 4, 5. 5 electron domains means it is trigonal bipyramidal. Bipyramidal. Our base structure looks like this. Actually, wedge dash. Now, because of the lone pairs need to be the farthest apart they can be, I'm going to put them here and here. That means I put the fluorine up top, up bottom, and right there. 3 bonds, 2 lone pairs, lone pairs up to 5. The shape right here is our T shape. I mean, that's what we got to do. At this point, yes. Is this a lot of work? Is this a lot of steps? Yes. But once we've done the lab 4, we should be fine. Lab 4 is just, you come in, you can hypothetically make some models. I'll walk you how to do it, but it's, you have a worksheet to be working in your group of 2. Draw them out. Draw them out. Put in all the lone pairs. Determine the electron geometry. Determine the molecular geometry. Figure out whether it's polar or not. And then let's look at like hybridization, which we haven't gone to yet. So it's a process, but you'll get plenty of practice with this process. Okay. Come on. Oh, yeah, that's probably going to be the problem. Yeah. Now, we can also look at geometry of large molecules. In fact, this is something some people need to understand when they think about enzymes and how proteins fold together, because you're going to have all these same basic geometries just expanded to multiple parts of the same molecule. This molecule on the left is acetic acid, the main active ingredient in vinegar. It's C2H4O2 or CH3CO2H. But right here, you can look at each carbon and each oxygen molecule and see its basic geometry. This carbon on the left has 1, 2, 3, 4 electron domains. And what shape does 4 electron domains have? Tetrahedral. Tetrahedral. You can see this molecule, this hydrogen atom kind of coming towards us. This one kind of going away from us. These two being flat. This carbon has 1, 2, 3 electron domains. 3 electron domains is trigonal planar. You can see the flat triangle there. By the way, these pink little things are lone pairs. So this oxygen has 1, 2, 3 things coming off. It's trigonal planar, but it's only really linear because it only really has one bond. And this oxygen has 1, 2, 3, 4 things coming off. It's tetrahedral, but because these are lone pairs, we are only seeing the bent shape. Now this molecule is what I'd like to say, don't get mad at me if I'm wrong. I think tyrosine, it's a basic amino acid. Either way, you have amino acid. Here's the acid component, which is just exactly like the acid component here. There's the amine component, which is the blue molecule, the NH2. Has 1, 2, 3, 4 things coming off of it. It's tetrahedral. But because one of them's a lone pair, it's trigonal pyramidal. Now this carbon right here has 1, 2, 3, 4 things coming off of it. It's tetrahedral. This carbon here has 4 things, tetrahedral. And this ring here actually only has 3 things coming off of it. Each atom on the ring only has 3 things. 1, 2, 3. This guy, 1, 2, 3. So on 1, 2. This whole part is planar, is trigonal planar. This whole ring is flat because of its trigonal planar geometry. That's the basic geometry of a simple amino acid. Each amino acid is going to have different shapes present in there. And this organic shape is going to like to match up with other organic shapes, and it's going to control how this guy folds in order to put all the organic shapes near each other. Well, if this thing had an oxygen on it, or a sulfur, or some sort of positive charge, that's going to change how the protein folds as well. But all these shapes, we can look at individual molecules and say, this carbon here has this geometry, that carbon there has that geometry. And don't be overwhelmed by the structure as a whole. You can look at each atom individually. As long as you remember, well, oxygens typically have 2 lone pairs. Nitrogens typically have 1 lone pair. Carbon typically doesn't have a lone pair, and you could probably get along just fine. One of the major things we have to think about is our molecular dipoles, and this is kind of important why we need the shapes. Now, earlier, last chapter, we looked at just an individual bond dipole. In fact, we looked at a homework problem or two on which of these bonds are more polar, where you looked at the electronegativity difference to calculate this. Now we need to understand the idea of vectors and opposing forces. A dipole is a kind of like a polar force vector that can be described by the coordinates x, y, z, and a strength based on the difference in electronegativity. Now, dipoles will be added and subtracted from each other depending on the vector coordinates. The main idea here that you need to take away is that equal and opposite dipoles will neutralize each other. What this means for us is that a molecule with polar bonds can be nonpolar overall if the atom is symmetrical, if the bonds cancel each other out. The bonds cancel each other out. I'm going to go back to the doc cam real quick so we can see this. We will probably see this some more on the next slide. But doc cam, looking at this structure, we have C is stronger than O. O is stronger than C. Totally backwards. So this guy is pulling away from the O. However, this O is pulling away from the C. And because they're both oxygen and they're both pulling the opposite direction, the net effect is a cancellation. If you have two sides equally strong pulling on a rope, like a tug of war, the rope is not going to move. The rope is not going to move. Now, this guy, water, because this is not the actual shape. The actual shape, remember, is a tetrahedral structure that we call bent. Now, O is stronger than H. So O is pulling up, and this O is pulling up on this bond. This guy's pulling right and up. This guy's pulling left and up. And because they're both pulling left and right, do cancel each other out. But up, they're both pulling up. So the net effect is a pulling of up. Say you're trying to haul a car. Like you have a little car, you're drawing my little car. Yeah, not the world's best car, but you have a rope. If one guy's pulling this way, pulling the rope this way, and one guy's pulling the rope this way, the car moves up as the rope tries to become taut. The rope essentially would eventually come this way, become flat as the car moves forward. If guy A is pulling left and up and guy B is pulling right and up, the car would move forward of that direction. That's the basics of the vector chemistry. You look at what all directions are being pulled and see which ones are the same and which ones cancel out. Let's look at our xenon, F4. Xenon has almost no electronegativity. F has some. F is one of our most electronegative elements. However, this F is pulling forward and right. This F is pulling backwards and left. Forward and backwards cancel. Right and left cancel. This one has a net pull of 0. This F is pulling up. This F is pulling down. Up and down cancel. The net effect is non-polar because all of the tugs on this rope cancel each other out. Looking at chlorine, we have one guy pulling up, one guy pulling down. They cancel. However, one guy pulls right. Is there anything pulling on the left? No. There's just lone pairs. So the net effect is it pulls to the right on the T shape. It pulls towards the feet of the T because there was no equal and opposite attraction. And that's one of the things we will need to recognize. That's one of the reasons why we kind of draw these structures to try to better understand this. Now, as I said, it is possible to have a polar structure and a polar bond and a nonpolar structure. All the top structures are polar due to what's called asymmetry in the shape and in the dipole moment. Asymmetry is the lack of symmetry. Like asexual is the lack of a sex. Asymmetry is the lack of symmetry. So, shoot, wrong thing. We will not go into that today. We will finish with this slide. I just wanted to adjust that. So what we have here in the structure-wise, we have HCl. Clearly, H and Cl are different. There is nothing opposing that, so that is just a polar structure. There's our water again. There's our water again. The net effect. This is dichloromethane. 2 chlorines. These hydrogens are flat and opposing each other. These chlorines would be opposing each other from the top and bottom side. However, they're both on the right of this molecule. So the net effect is it pulls to the right on this molecule. This guy on the bottom is carbonate. Each oxygen is stronger than the carbon. However, if you look at this, this is a perfectly symmetrical molecule. It's a fidget spinner, essentially. You spin this oxygen can go to that oxygen's place. We can shift them all down. We can fidget spin this around, and each oxygen is equivalent. It may not look like they perfectly oppose each other, but they do. This guy is just pulling straight up. This guy's pulling left and down. This guy's pulling right and down. Because of the angles, left and right obviously cancel, but the 2 downs are at a fraction of the up. But the 2 downs add up to cancel the up. if you calculated the heights based on what, like the Pythagorean theorem, you would find that the directionality from the B, the side, the downside would add up to be that bond angle. You could figure that knowing what the bond length would be. But we're not going to actually do that. The idea is perfectly symmetrical molecule always cancels out. CO2, that's a pretty darn symmetrical molecule. You could spin this around, and that goes to there, and that goes to there, and it's the same. This guy is what, like SF6? Something like that. And what we see there with SF6 is this guy cancels that guy. That guy cancels that guy. That guy cancels that guy. Even though each bond is polar, the net polarity is all canceling out. So anything that's perfectly symmetrical where the atoms cancel each other out is nonpolar, even if each bond is polar. However, there's one other trick. If no bond is polar, then it's also nonpolar. Even if there's asymmetry. Even if there's asymmetry, if the bonds aren't polar, then the molecule can't be polar. I'm going to give you just one quick example, and then we're going to go. And this is, so remember, carbon monoxide, that is polar. We draw this, boom, boom, that's very polar. If we did that, but carbon, the sulfur component of that, CS, I'm not sure this actually exists. You can't really see due to the glare. Let's see. Due to the glare. But carbon has a polarity of 2.4, if I remember right. Sulfur has a polarity of 2.4. The difference between these two is 0. So these are non-polar bond. Even though this structure, the electrons get pulled towards the oxygen. This one, they are the same. So they do not get pulled anywhere. They're equal sharing of electrons. There would be the equal sharing of electrons in that case. So we have to look at both the electronegativity difference and the shape to determine overall polarity. Now, that is where we're going to stop for today. Thank you for your time. Don't forget to turn in your test. I'd like to have those tests before we start losing any more points.